thanks a lot for coming here, and thanks a lot, Volodya, for agreeing to talk again. So we're very happy to have today Vladimir Fock, and he will be speaking about tau functions, whatever that is.
It is, yeah, exactly. So thank you very much, and I'll speak about exactly tau functions. And what I'm going to speak is very probably that I'm not pretending that I'm speaking about something really new. It's maybe new insight, but some old things. And for me, for quite a while, the notion of tau function was kind of a zoo where you have many cages, you have some of small elements, animals, big animals, and each animal, well, sometimes they resemble each other, sometimes not. So it's just class of object which is rather large, and well, all the definitions were different. And so what I'm trying to do today is just to give some definition of tau function, and well, some formulas for that, which are well, kind of universal and kind of point of view on tau functions, which is well, related to, well, finite gap tau function, so related to Riemann surfaces, which is a kind of universal story. Well, well, for those who are not familiar with tau functions, so tau functions essentially some functions, well, the most typical tau functions which you, well, for KDV, for example, you have a function tau, which is a function of infinitely many variables, so T2, T1, T2, so the function of infinitely many variables, T2, etc. And such that if you have a well, this is a generating function, so tau is generating function for Kp, for Kp, for example, in this particular case, for Kp, and if you have a function, well, if you have sine Gordon, then you have double set of times, and if you have some, well, for some other systems, you have integer variables inside it, so it's just quanti-zoo.
So those scary letters, that it refers to some integrable stuff, right? We're not supposed to understand what Kp means, right?
No. For a moment, it's just some PD. Mm-hmm. You, well, certainly you do not.
Okay. We don't, yeah.
I would just, well, and the main difficulty with tau functions is just sometimes it depends on one set of variables, sometimes it's another. So, well, kind of, sometimes it's discrete, the integrable equations are discrete, sometimes they are continuous, so this kind of mixture. So what I'm going to construct is, well, to define, it will be, well, some definition of tau function, and moreover, well, another thing that's the standard definition of tau function is kind of uses the fermionic representation. And I'm going to do the same thing, but with bosonic representation. So it's just, well, more or less bosonic definition of tau function. Bosonic definition of tau function. So, well, now I need to prepare a little bit for this definition, and then, well, first think that, well, definition. So see if sigma is a Riemann is a complex Riemann surface, not necessarily compact surface. Then I will denote H of sigma. So this is space of, or group, maybe it's better to write it, denote as a group. Of quasi-meromorphic function. So quasi-meromorphic function, so it means that so functions of the type, so locally having the form f of z is equal to r e to the phi, where r and phi just meromorphic. So this is a slight generalization of the notion of meromorphic function. So you allow not only meromorphic, not only poles, but exponentials of the poles.
Sorry, when you say a group, you want to add them or you want to multiply?
Group with respect to, so yeah, this is a group with respect to multiplication. It's not a vector space, because if you add to such functions, so as a form a group, H is the claim, H is a group with respect to multiplication. Well, what is hopefully clear, another thing that any f of z may be so locally, also locally, around 0, any such function can be written uniquely as z to the k times exponential of the sum of tk z to the minus k. So this is a sum over k, zl, sorry. So of course you can, well, this is any meromorphic function, but well, any meromorphic function is a power times something equal, well, such times which you can compute the logarithm, so you can always represent in such a way.
Volodya. So
Yes.
L is just an integer, right? Positive or negative?
Just a positive, yeah.
And K, so the summation
And K is
from...
Yeah, K is, well, is greater or equal than some n, which is depends on, less or equal, sorry. I wrote maybe.
Yeah,
sorry.
so it's in secret, it's a, okay, it's a Laurent series, so it
Laurent series, yeah.
Lower bound, there is a lower bound on K, is it right?
Yeah. There is a lower bound of K, but not upper bound. Well, we'll consider also the functions with upper bound, but nevertheless, well, something which, well, this form is independent on, well, of course, if you change coordinates, then the coefficients t change. But so this representation really depends on the numbers t, depend on the coordinate system chosen. But nevertheless, well, once it's chosen, you can just parameterize this group H. So this group H locally is, can be represented as a, so to say, product z times c and infinitely many copies, z times c to the power infinity, well, to the power n, or z, I don't know. And we have one integer coordinates and infinitely many.
Sorry, why n? Why not z? Because a priori, right? It can
well, maybe z better. Yeah, you're right. Maybe z better, but yeah.
You're not that picky about topology, right? So it's okay.
Yeah, right. Maybe z is better. Or something countable anyway. So this group is called H. This group H contains H. Well, let's take HP, but by definition, just specify HP is a group of where P is in our surface sigma, is the group of.
Sorry, if I may, one more question. So, but we want them. So these are functions of that form, but all those series, right? They are well defined. You mean they converge in some?
They converge. They converge.
So
somewhere. Here, we have a. If I write h of sigma, maybe I should write always this sigma.
Yeah.
And h of sigma should be a function on sigma minus finitely many points.
Finitely, so there is a finite number of singularities which are of that type.
Yeah, exactly. There are finitely many singularities on all points. Well, it's a function defined everywhere. So h of sigma, maybe I should write it explicitly. So h of sigma is defined, is a function on sigma minus finitely many points. Finitely many points. Is the group of one moment. The group of germs of H of quasi-meromorphic functions around P. So it's just a group, and the coordinates on this group are just h of, maybe respectively I can write this as h of P. So if I describe the germ of function around the point, so it has these numbers at coordinates. So what's the most important is the following, that, claim that this group HP has a central extension, the cocycle. Defined by a cocycle.
Group extension.
Group extension, yeah, of course. It's just a abelian group, but the extension is non-abelian. By a cocycle, and now such the formula for the cocycle is the most important. So I'll write in different versions. So in order to, I'll try to just copy it from the in order to have the formula, which is, there are several definitions. One of the definitions is the following. Let me try to insert the. Okay. No, sorry. Sorry. Well, I didn't manage to move it, but I hope it's visible, this formula. Can you see the formula, by the way?
It's visible.
Visible. Okay, thank you. This is a formula. There's one formula for that. So it's just CP is just something which, CP is a function which sends HP cross HP through Z to C. And it's given by some integral, which is, more or less log F d log G, though there is some additional term here. And the claim is that this formula is well defined. So what gamma is gamma is a path around zero.
Sorry, but now we only have a singularity at zero, right?
Yeah, we only have a singularity at zero. Yeah. So CP is really defined. So its f and g are just germs of my function. So they defined in some vicinity of zero.
Now, what is this log g gamma of zero dot? Dot is over what and how?
Dot, it seems to me that dot is something I should erase. Yeah, it's just that.
Okay.
So this is there is, this term is just log f d log g, but log f actually is not well-defined function because it's defined only up to 2 pi, and if you just take this first integral, then this integral depends on the starting point of gamma because the branch of log depends on it. So the claim is that if you take this difference, then it doesn't depend on the starting point. Another point of view on the same, you can just represent f and g by introduce the coordinates for this formula, and you can write it in another way. So suppose that you have, I'll do another, try to show another formula, and the other one is the following one. So one moment, if it goes correctly. No, it doesn't work. No, sorry, one moment, cancel. I'll write down maybe.
What about examples? How the cocycle looks on some simple f's and g's?
Yeah. I will rewrite maybe the formula. You will recognize it. Yeah. So this is this is not very complicated as a cocycle. So I will write down the following. So if you have a function f, which is the sum of f is z to the k exp of sum of t minus I z to the I, and g is equal to z to the L exp of sum of p minus I z to the I, then C0 of f and g equals just exp of k p0 minus L P0 plus some P I T minus I. So this is something which is more or less the simplest possible. You can write down antisymmetric in these coordinates.
And I is non-zero in this. And I is non-zero in this.
I is non-zero. Yeah. I is non-zero. Thank you for the remark. R is non-zero. So the term, the zeroth coordinates is paired to the integer coefficient, but however, the rest is just sum over non-zero coefficients. These two formulas are both very important, and maybe I'll speak a little bit about this formula as well. How one can interpret this formula in another way. So there is some geometric interpretation. Yeah.
Sorry, just from what you write, does it mean that this is some kind of infinite dimensional Heisenberg group?
Of course, it's just, honestly, it's nothing new. It's just usually one writes a Heisenberg algebra. Here is just Heisenberg group. So this is the exponential of the ordinary Heisenberg algebra. is just a group element of Z. Somehow this formula is not very popular, though Heisenberg algebra, of course, is very well, it's used everywhere. This formula, as all that which I'm speaking today, I was proud to find it myself, but of course it was known before, and I was shown that maybe the first time this formula appeared in the text by Benenson. Whatever, but well, how one can, well, so there is some geometric interpretation of this form. Since it's cocycle, well, which we'll use extensively, so I will nevertheless, it's useful to use this formula in plenty of different ways. So geometric interpretation. So consider the following space. So let's take the space C times C times C times C and quotient by Z cubed, which is given by the following action. So A, B, C, X, Y, Z goes to X plus 2 pi I M, Y plus 2 pi I N plus X M, Z plus 2 pi I L. So there is a well, you have C cubed, and you have the group Z cubed, which acts on that. But well, there is a such element which sorry, maybe I'm wrong in this formula. Sorry, I'll just rewrite a little bit. Pi N Z plus 2 pi I K plus X times M. The claim that the form dz minus x dy, maybe you should met, is invariant under this section. Well, you can verify explicitly that this is invariant. So therefore, it defines so well now. Pardon?
Yeah, I have some. I'm not sure. Kind of, is it really invariant? Because in dz you get this extra term mdx, right? And how are you going to compensate it? Because the other term will be anyways proportional to dy, whatever you do, right?
You have mdx.
Could it be n? X could be multiplied by n here, perhaps?
Is it? Yeah, maybe n. Yeah. So sorry. Well.
No, you probably should multiply m by y. And
Yeah.
then
Why looks so promising?
Ym. Ym. Yeah. One moment. I'll just look at my notes. Y. So you have dy, and this have This is maybe y times m. So if you shift that by that, you see m dy, and here you have m dy with minus. So you need to have 2 pi I here also. or divide dz by 2 pi I.
It's a Heisenberg contact structure.
Yeah, it's just standard contact structure. Well, yeah. So what you get finally, you get at the end, this quotient can be represented as some space E, which is mapped to C star squared, and the fiber is C star. So this C star squared is parameterized by e to the x, e to the y, and this x is parameterized by e to the z. So you have a map. You have finally this space E is a vector bundle, is a line bundle, C star bundle with connection. Over C star squared. Now, suppose you have so where the connection is not flat. The connection, well, if you introduce the coordinates, if x and y are big, so this is an element of C star cross C star, then the connection form is, of course, just given by this formula, is just ln of x, dln of y, or 2 pi I. Well, the claim is the following. So if you take, let's consider well, we constructed therefore the vectors, well, the space with connection, and now let's consider the map. Two functions, two functions f and g, is just the map from C star to C, or C star, the local map defined around the 0, and let's consider the following thing. So we take this form alpha. There's a connection form, and well, what we can do, we can take the map F. One can consider FG, the pair FG, as a map from C star to C star squared. And here you have a map E, so you can pull it back on C star. So you get the, well, the FG star applied to E, C star bundle with flat connection. Why it's flat? Just by dimensional reason, because the connection form is a one form, and you have, and the curvature is the two form, and you have a homomorphic map to something of dimension, well, on one dimension we can have no curvature at all. So therefore, we can, the C, by definition, C of Fg is, well, the monodromy of the connection in this line bundle, Fg star of E. Well, 0, for example. So I interpret, well, and this formula, which I wrote before, this, well, the formula, this one, is just the, well, it's just this monodromy. You just compute it, well, understanding that the line bundle, which is your computing the monodromy, is non-trivial, so you need to adjust the integral of the form by some additional term. So I want to say that this comes from some natural reason. So now the properties of C0, properties of this cocycle, of F and G. So some property you can compute explicitly. So one is, of course, a cocycle property. Cp is a cocycle. So Cp is a cocycle of Fg is equal, well, maybe Cp minus 1 of Fgf. It's skew-symmetric, it's not necessary. First one. Second one, Cp is a cocycle. So therefore, you can define the group. So one can define the map. One can define the group HP hat. For example, like element is pairs, as element of pairs F X, such that F in H and X in C star, and with the multiplication Fx times Gy is equal to Fg comma X Y C P of Fg. Just the standard thing, and well, the associativity of this product is amounts to this property of third property, which is actually the most even stronger than the cocycle property, which is satisfied by this function. This is bimultiplicative. So Cp of Fg H is equal to Cp of Fh times Cp of GH. So this is well, more or less also easy to using this formula is very easy to verify. Of course, it's well, this property implies that it's multiplicative with respect to second argument as well. And now the fourth property, which is maybe well, until now we have everything with just the vicinity. We're speaking about the vicinity at one point. Now there is a property which is just kind of global story, and the property is the following: that Cp of if you have two functions f, suppose that f and g are just quasi-mirror function belonging to H of sigma, where sigma is a compact Riemann, closed Riemann surface. Then, if you take the product of over all points P in sigma of Cp of Fg, it is equal to 1. Well, this formula can be called while reciprocity.
So what's the meaning of it? You mean it's actually a product of the finite number of points where F or G have singularities, right?
Exactly. Of course, maybe I should also write that 3.5, the property of 3.5, that if you have F and G are homomorphic, then F CP of F and G equals 0.
Sorry, we don't see it there.
Pardon?
Yeah, now we see it a bit better, but you're writing on the part of your pad, which, yeah, now it's better.
Yeah, I'll try to CP if...
And this is 3.5 because it should precede 4, right?
It should precede 4, yeah, exactly, for this reason, yeah. Yeah, exactly. It's more... so we also can define the group HP plus is just the space HP, and this HP plus is well, it's just a homomorphic function. So these are F in HP, F homomorphic. And of course, HP can be also considered as an element of H. Well, P belongs to, one can embed it naturally to HP hat as well. Since this is well, now I'll just mention what actually the proof of 4 of this property 4. After what I have done.
Sorry, I have one more stupid question. So, is it correct, as far as I recall? So this power k in z to the k was in the pairing with t naught. Was it right? Or
right? Exactly. Yeah.
But then t naught is in front of a constant. So in principle, z to the k times exponential of 5 or whatever, exponential of some constant, right? It's still holomorphic. So why do you say that C naught of FG for 2 holomorphic ones?
Maybe I should mention, sorry, thank you very much for the question. Homomorphic in non-zero. So therefore, z to the k must be 0.
Okay.
So this I do not allow the power.
Okay.
So log should be homomorphic. Yeah, thank you for this. Of course, the z to the k part belongs to the complement of HP. So what's the property? What I have done after this geometric interpretation, this is very, very straightforward. The proof is very easy. So if you have a map, so suppose you have 2 functions f and g, we can try to do the following. You try to take the f star, maybe I should, f and g, the pair, gives you a map from your surface into c star squared. And of course, you can construct the f g star of your line vector bundle, line bundle E is a bundle with a C star bundle with connection which is flat outside singularities, singular points. So outside the points where f and g have poles. So, well, we know that the product of monodromies of E around singular points is equal to 1. And therefore, well, and this is just my theorem that, well, this Euler reciprocity, that the product over the points of CP of G is equal to 1. Is just well, somehow a little bit advanced form of the standard residue theorem. The sum of residues is 1, but this is a multiplicative version. So this is a kind of, after this, why I needed this geometric interpretation to make this reciprocity, Euler reciprocity property obvious. Euler reciprocity is also, well, strictly speaking, in Euler paper, it's done for only for meromorphic function, not quasi-meromorphic, but the proof doesn't change. It just goes exactly the same thing for quasi-meromorphic as well. Well, this is now, well, I more or less finished the discussion of what is the CP. I want now to pass a little bit to tau function. So first of all, remark that the HP hat has a standard.
Sorry, just a question.
Yeah.
Since you said that, you know, finish the topic, of course it's slightly early-ish, but I mean, is it a good point to make a break and then embark on tau functions just after the break?
Yeah, I was thinking about that. Well, so 43 minutes is normal. Yeah, okay, let's make a break right away. Yeah.
Sure. Okay, that sounds good. So then I suggest we have a break, maybe a coffee or whatever, or whoever prefers what, and then maybe we just reconvene at 4.
At 4K.
Yeah. Okay.
Mm-hmm.
Okay. Sounds great.
Okay.
Thanks a lot. Sorry for like stopping you in the middle of writing the phrase, but I mean.
Yeah. No, it's a good idea. Yeah. I just didn't pay attention much to the time.
Okay. So then it's a break.
Great.
I had a question. Continue.
Okay. So now my game is my aim is to construct some representation of HPP hat, and well, this representation I'll maybe before doing that I'll make, well, I repeat in fact some definition a little bit different version. So HP plus hat.
Nikita, do you understand what happens?
I think
he lost connection.
I think Vladimir's internet is unstable. Yeah.
Mm-hmm.
Or maybe his computer froze. One or the other, or maybe both.
Okay.
Let's wait and see what happens.
Right. Well, that depends how much time passes until he notices.
He's back.
Maybe you unmute him, right? Because I think now he's back.
Yes, he's just returned. Hello,
Yeah.
Vladimir.
So okay, hello. It's something. Well, it's every 40 minutes, or do you see me?
Yep.
Oh, yeah.
We see your pad.
Yes.
Okay, wonderful. So I have you have HP. Well,
wait. We haven't heard what is HP plus. So that all this.
You haven't heard. Sorry.
No.
HP plus is the pairs of just HP plus hat. It's just pairs F and X, where F is homomorphic and F is homomorphic. X is whatever complex number. And HP minus is just quotient of HP by HP hat. HP hat plus, which is also, of course, without hats, it's just the same thing. HP quotient by HP plus, and this is parameterized by HP minus is parameterized by the integer, which is k, and then T1, T2, etc. So positive coefficients, the quotient. But well, remark that these coefficients really depend on, so this parameterization depends on the coordinate system, on coordinates. So this, well, if you change coordinates, the letters T change. Now we have a map, rho, which is map HP plus to C star, which sends rho, which sends Fx to X. So this is a standard homomorphism, and if you wish, a one-dimensional representation of HP plus. And then let's define BP.
I forgot, what is X?
X, well, element HP plus is a pair of, well, H hat. Sorry, it's hat important. Hat is
oh, that's
central tension. So it's central element.
So
X
that's the central part, right? Okay.
Just central part. The central part is, well, the function goes to 1 and central part goes to itself. It's just the most naive representation one can imagine. Now let's define BP as we take the induced representations from HP plus to HP of rho. Once again, what is BP? BP, well, one can imagine that as a functions, so it's functions of on HP hat satisfying the following relation that V of F times G is equal to V of G by definition times Cp of Fg. For F in H plus. So if you multiply F by a positive element of F, sorry, it's not comma, it's times G. It's just a definition of induced representation. So therefore, the value of the function, this BP is essentially isomorphic to, one can interpret this as well, isomorphic. Well, it depends on, the isomorphism depends on, well, it's not canonical, but it's isomorphic to functions on HP minus. Because we know if you multiply by HP plus, we know how our function changes. So therefore, if we have a section of the bundle HP of HP minus, then we can, well, it's not invariant under the action of HP plus, but it's covariant. So it's defined by its value of any section of the projection. So you have projection HP to HP minus. If we fix a section, sigma, then the value of V is determined by its value of the section. So once again, this can be interpreted only if we fix a section, if the section is fixed. Sigma is fixed. For example, if we fix the coordinates, so we fix a coordinate around Z, around P. Well, now after doing that, well, I'm very close now finally to define the notion of the tau function. But before I'll do the following. Let's take the following thing. Well, another observation. Let's take just the product over all P in sigma of HP hat. And well, this is a del product. So it's a collection of elements of HP at every point. We suppose that it's equal to 1 for which is holomorphic of almost everywhere. So this is a product. There are elements of, it's actually in HP plus everywhere except finitely many points.
So sorry, for the del product, how is it a different piece? They're not necessarily specializations of the same function, right?
Not necessarily specialization of the same.
Now this is just like at every piece, there is a finite number of p's where we have some kind of independent singularities which are not related to each other.
Right. So singularities are, yeah, they are not absolutely not related. And of course, this, if we have this product, then this, sorry, I'll pass to the next page. So HP, well, that this group, this acts on, you have also tensor product over, well, this is a product, maybe not tensor, but just usual product, it's something like that. If you take the tensor product of BP, then of course, the same thing, the Adel product over P in sigma, then the HP acts on this, on that, it's obvious. Well, just now, remark, observation, well, strictly speaking, the observation is the following, that HP, H of sigma, without a hat, is a subgroup of this tensor product, of the product of BP, no, HP. What is important in this statement, that here we have no hat. So if you have a global function, then you can decompose it at every point, and therefore consider global function as some element of this product of HP hat over points. Now I claim that if you take restriction of the central charge on this product is equal to 1. So this image of H of sigma here is not centrally extended. And the reason for that is a consequence of the Weyler reciprocity formula. So it's exactly tells about Weyler reciprocity. I can return a little bit back. So that if you have the product of all points or the central charge computed on two functions, the product is equal to 1. So if you have two global functions, then the central charge product of central charges computed with them is equal to 1. Maybe I should also mention one thing which is my notation are not very good. So perhaps it's better to write here as a product, write here HP, we put hat over everything. So it means that you take the product of HP and you have one central charge for everything. So it's just one-dimensional central extension of the product of HP without central. So this is just one central charge for everybody, and the same thing here. So here you have this hat over everywhere. Now I can define.
Sorry, but then actually, how does it work? Suppose I have 2 points, P1 and P2. I have the 2 functions, right? At each point, I multiply them, and I get a cocycle at one point and a cocycle at the other one. I simply multiply them.
You multiply the cocycles, yeah.
Mm-hmm.
You multiply the cocycles.
Okay.
Yeah, thank you. Yeah. Now, definition, finally. What is a tau function? Tau is just, you take the space BP, tensor product over P, and then you take H of sigma invariance. So tau function is an invariant of you take this big representation, idyllic representation, and you take the vector invariance with respect to H of sigma. This is the existence. Well, this for this vector to exist, it's necessary for this property is necessary, because if it were not necessary, were not true, then we couldn't have invariant vectors with respect to subgroup if there is a central extension. So, however, central extension is 0, so therefore tau has right to exist. Well, the theorem, which is kind of I'll try to start to prove it, but nevertheless, tau, the claim is that tau, the space of invariance, so this space is one-dimensional. So now, sorry. How to interpret this function? So first of all, what is Z? So BP is the tensor. How one can imagine what this function looks like. So BP is a space of functions. So tau is a space of functions. Depends on tau is a function of infinitely many coordinates. Which coordinates so for every point we have the function p or p1 k1 t1 p k T2 P, etc. So it's a function of infinitely many variables. So for every point of your surface, you have one integer variable and all infinitely many continuous variables. But you should understand this thing is an extent. So you have this function, you can restrict it to the set of variables, which is just, you have finitely many points and finitely many variables at each point. So this is a collection of functions of infinitely many variables, but actually is defined by its value on any finite subset of these variables. And I'll write down some geometric interpretation of that for a moment. So once again, one should define what is a tau function. So geometric interpretation. And for that, one can define something, give another definition, which is kind of be useful for not only for this thing. So let's define consider the space which is, a little bit generalized notion of divisor. So quasi-divisor is a collection of elements of HP minus for finitely many P in sigma. So you have finitely many points and finitely many elements of HP minus. I just, since, well, HP minus, it's the HP plus, HP, sorry, quotient by HP, quotient by HP plus. And this is something which is parameterized by K, T1, T2, P, etc. So you have on your, well, this definition depends on the coordinate system. This definition does depend on coordinate system. So HP quotiented by, sorry, there is no, well, the usual divisor is a particular case of the quasi-divisor. In the case that you have just ordinary meromorphic functions, so all t's are equal to 0. So we have just a collection of points, every one with some integer on it. By definition, the degree of a quasi-divisor of Kp, T1, T2, etc., is equal to Kp. So the degree of divisor is just the order of the pole, which is absolutely correspond to the ordinary divisor. Now, so if F, observation, if F is an element of H, well, definition, it's rather not observation, but definition. F in H, then the quasi-divisor, the F is a quasi-divisor of singularities of F. So if you have a global function on sigma, then it has finitely many singular points, and every singular point you can remember only singular part of F. So it gives you exactly this quasi-divisor corresponding to this function F. And very easy proposition, which can be proven exactly the same way as you prove the ordinary proposition, that if you take the space of quasi-divisors, this is a space of quasi-divisors, space of sigma, of quasi-divisors, and you quotient it by the space of principal quasi-divisors. So, sorry. So principal quasi-divisors. So the quasi-divisors which are of the form F, for some F. Of the form F. So if you take this quotient, then the result actually doesn't is not absolutely the same. So it's equal to just the picker of sigma. So the result doesn't change if you change the notion of divisor by quasi-divisor. It gives the same thing. Now, I want to say the following, that the observation that tau functions can be interpreted as a function on Q div. Well, to see. So the tau function is a function on the space of quasi-divisors, because why? Tau function by definition is, any function, any element of not only tau functions, but any BP, the space of BP tensor over P is just the space of functions. It's just a space of functions on quasi-divisors. In particular, tau is a function on the space of quasi-divisors. But tau is not
space
any
of
function.
quasi-divisors or principal quasi-divisors?
Thank you. Quasi-divisors, of course. But tau has the following property, that it's invariant under this subgroup. So under this subgroup of H of sigma. So you can write it down and compute this invariant property. And it's some computation, but a proposition that invariance of tau can be written in the following way. So if you take tau of a quasi-divisor Q, and you add to that a quasi-divisor F, then it is equal to, it's just, this formula which I'm going to write is just a consequence of the invariance of tau from which I defined a little bit earlier. So Q plus F is equal to tau of Q times C of product over P, Cp of Q comma F squared times Cp of F plus F minus. One moment, what's the definition? First of all, if we present if F at the point P is equal to F plus F minus, so F plus in H plus, and F minus is some complement of F minus.
Sorry, on the left-hand side of your equation. So the addition of divisors is multiplication of functions?
It's multiplication of functions, yeah. This is a multiplication of functions, but here is just divisor. So it doesn't, globally, it doesn't correspond to any function, this quasi-divisors. On the other hand, here it's also some, abuse of notations. So here I compute the function locally. So here I strictly speaking, Cp of Qf is equal to Cp of Gf, where G is some function such that G is equal to Q at P. So locally, you can represent any quasi-divisor as by a function. So you just represent this quasi-divisor by a function, and then you compute this and well, of course, you need to verify that this equality doesn't really depend on all the choices made, because the product of a plus and minus is not canonical. The choice of a function representing Q is also not canonical. But well, if you verify everything is well, all this non-canonicity goes away because of multiplicativity of CP and the property that it vanishes on homomorphic part. So there is, well, this formula is.
Sorry, I'm still a little bit confused. How is it? So when you choose the representative G of Q at a point P,
yeah,
right? This representative you can change locally without any changes at other points, right?
Right,
so
of course.
This is so therefore, so this CP of QF a priori may change when we change just this representative, and I don't see how it would be compensated by anything, because there is nothing else which changes. Just maybe naive, whatever. Like.
Right. One moment. It's just well, I will maybe I should write in a little bit different way. I don't want to write too complicated formula. One moment. I'll. Sorry, for of course, this here is F, yeah, right. If here is F, homomorphic function, so it's yeah, if it's you take the minus part of that, right? Well, this term and this, if you change the coordinate system, this term and this term changes at the same time, and they compensate each other. However, if you change Q, what means that you change a Q? You change Q by some homomorphic part, and the homomorphic is minus plus. Sorry, if you change the Q by homomorphic part, it just gives you 0 with respect to this F.
Oh, so sorry, you're saying that you only take an F plus?
I'm taking only F plus, yeah.
Okay, that sounds good.
Yeah, it's so. Well, this is also once again, it's just a computation directly from the induced representation formula. What is induced representation? Well, this is a computation, so it's what it tells you, that if you add, you take a homomorphic, well, take a quasi-divisor, add a, you know, well, maybe you should draw the phonic picture. So you have the space of quasi-divisors. I'll move it a little bit around. So this is quasi-divisors. Sorry, Q div. Here is the, well, maybe I should write down the Q div 0. So Q div 0, it's just the quasi-divisors of degree, quasi-divisors of degree of degree 0. Then if you take a quotient with respect to,
sorry, what is the degree?
Degree, I just mentioned that the degree of somewhere, the degree of quasi-divisors is of, well, quasi-divisor is a linear combination. Well, it's a sum, it's collection of this expression k, t, t1, etc. And degree of quasi-divisor is just k.
Okay.
It's something which doesn't depend on t's. So you have a collection of points, everyone well, equipped with integer and complex numbers. So the degree takes into account only the sum of these integers. So and we consider the yes, and then you just here you have the Jacobian, because the quotient of quasi-divisors over of degree 0 over quasi-divisors principal. The degree of principal quasi-divisor is also 0, so it's subgroup for the same reason as happens for the ordinary divisors. So this is equal to the Jacobian of sigma. So you have a Jacobian, and you have fibers of this map. So of course they are infinite dimensional, but this formula shows you how tau changes if we move along the fibers. So therefore, the space of solutions for this equation, I would write, well, this star, the claim is the space of solutions of sigma of star is isomorphic to a section, homomorphic section sections of a line bundle over the Jacobian. So Jacobian is a compact manifold. So you have a line bundle over a compact manifold, and just by construction, this is the space of sections is finite dimensional.
What line bundle?
The line bundle is defined by this formula, essentially, because, well, one can define it in the following way. So let's take, well, how one can define it. Let's take, well, this you have an infinite dimensional bundle over the Jacobian. So the fibers are principal quasi-divisors. Let's take, well, this fiber bundle, infinite dimensional fiber bundle in general, has no sections, but it definitely has logos sections. So you can take the coordinate patches, and every coordinate patch you can lift to some local section of this infinite dimensional bundle. Now you can so knowing tau function, for example, you may consider, well, knowing tau function on this section, so you can take tau function and restrict it to this section. So the sigma alpha, you take the tau function and restrict it to sigma alpha. And also you can take tau function and restrict it to sigma beta. So this is beta, and you take tau function restricted to sigma beta. And you know that the ratio of tau functions, tau sigma alpha divided by tau function of sigma beta is something which you can compute using this formula. Because you know how knowing functions here, you know that this value of functions here is just, well, this ratio will be something you call U alpha beta. The ratio of tau restriction of tau function here. And the claim is that U alpha beta is a cocycle defining the line bundle. Well, this is some standard way how you can get line bundle. So you have a if you had, for example, there were no this term, so tau function would be invariant under that. So the fiber bundle will be trivial. So you have just line bundle. So the functions invariant under the action of the group is just the same thing as a function on the base. Here you have some cocycle, and this cocycle amounts to the fact that the function which is covariant with respect to the group action are actually correspond to not to the functions on the base, but to the section of line bundle. And the the transition function is defined by this ratio, and this ratio is actually given by this formula. Well, I don't know if this is more or less clear what I did explain for that, but it's some such standard way how you can get not trivial line bundles out of group actions. So, well, of course, in order to prove the theorem, which I claim that the tau function is essentially unique, you need to prove that the Chern class of this line bundle is given, so that it's really the space of section is one-dimensional. Well, unfortunately, I don't know any simple proof for that, but this is some additional thing which you need to prove that the Chern class is equal what it needs to have one-dimensional line bundle. So finally, this is a definition. So the particular cases. So therefore, in a sense, tau function now is a function which depends only on the surface, but on the space, it's this function on a huge space. Now, namely the space of quasi-divisors. But, well, somehow, though it's a space of quasi-divisors, but this function is essentially the non-trivial, depends non-trivially only, then you move along the fibers. It changes trivially. The non-trivial behavior is you move along the Jacobian. So though it's a function of infinitely many variables, but non-trivial dependence on only finitely many variables. The rest of dependence is given by the formula which is here. So particular cases we can take the Riemann surface, for example, if you have a Riemann. So if you have tau and you take the surface which is just of 0, comma T1, so you have a surface and just one point on it. And at this point you have 0, comma T1, T2, etc. So in this case, T1, T2, etc. So this is Kp tau functions. So one thing. The second thing, well, if you have your surface sigma is hyperelliptic.
Sorry, and this Kp case, one can't say any, like, kind of, if you're not saying anything explicit about it, this means one cannot basically say anything explicit.
No, you can write down the explicit formula for that.
Okay, but it doesn't naturally come out from your formalism, or what?
It does. It does. Well, maybe I'll write it down for another particular case, but okay. I write down explicitly the formula.
Okay.
Not for this case because, well, I'm kind of not do not remember it by heart, but I write down the formula for another case. Well, if it's hyperelliptic, you can, well, yeah, and you have the same thing, and this point is actually so P is invariant point, so a ramification point. Then tau of well, here you have the point P, and you have also 0, 0 T1, 0 T3, etc. So you take only odd variables. So T of 0 T1, 0 T3, etc. is the KdV function, tau function. Another thing that you have, well, just for connoisseurs, you can take the following thing. You have, for example, for Kp, you take one point which is called P and another point which is what I'll call W. And at this point, you put just 1, comma, T1, etc. And here we have -1. Well, maybe I should redraw, sorry. You have the same thing as Kp. You have 1 point P, and you have -1, comma, T1, T2, etc. And another point, W, with coefficient 1, comma, T1, comma, 0, 0, 0, etc. And so this function will be tau, which depends on, of course, depends on P implicitly, but it also depends on W and depends on T2, T1, T2, T3, etc. And this is actually, it's a Baker-Kaiser function. So, for example, the property that if you approach W tends to P, then this function is has some essential singularity at this point, is a consequence of this previous formula, which I, well, the formula star. So this is the standard definition of Baker-Kaiser function comes from this definition. And finally, perhaps I'll write the formula, which is, well, I have no much time, but nevertheless, I want to always to write it. So number 4, this is a situation then if you have a surface and you have a finitely many points, but without t's. So you just have collection of points, P1, etc., Pn, and it's this every point you have, well, you have actually, well, you can ask what is tau function for ordinary divisors, not quasi-divisor, but ordinary divisors in a particular case, or all t's are zeros. So you have, here you have K1, well, here you have K1, K2, etc., Kn. So you have tau of P1, K1, etc., Pn, Kn. And there is a standard formula. This is you take the theta function, which you choose it a odd theta characteristic, and you take the sum of Ki Pi. Of course, you need that sum of Ki is equal to 0, otherwise it's not defined. So this is so you have this one times you take theta q of Pi minus Pj, the product over I less than j, to the power Ki Kj. All other functions can be written, all other tau functions can be written more or less the same way. So this is once again, this formula is a consequence of the formula star. So this follows from this star, and you can derive this formula. Well, theta q is a function. Well, theta q is a theta function. And q is an odd theta characteristic. Well, this tau satisfies, for example, well, in particular, it satisfies the discrete Hirota equation, which is also easy. Well, all these functions satisfy Hirota equation, which I do not write it down explicitly, but here, well, yeah, one can write it. And these tau functions correspond to actually discrete integrable systems. So this corresponds to discrete integrable systems. For example, well, I don't know, what is your favorite discrete integrable systems? For example, the pentagram map. that is well, in general, theta function looks like always it's just theta function of something times some quadratic form. This can be e to the quadratic form. Can be, well, one can interpret this equation as e to the something quadratic in case, and it's always the case. So it's theta functions times e to the quadratic forms in case and t's in general. And perhaps the very last remark, then, well, also there is apparently some relation which I'm not understanding at all, but I'm trying to figure out, that you have this formula for the cocycle, which I started with many well, this is a well, this cocycle, well, this formula or this formula or that, well, maybe this formula. And there is a very similar formula for what is called the principal symbol. So it's so symbol which allows to compute the extensions of the reciprocity laws, higher reciprocity laws for non-Archimedean field. So it's the formula from Kummer formula from number theory, and it's given exactly more or less by the same expression, but very similar expression. And it looks like well, I hope that it could be some relation in number theory, but I am not really expert in number theory at all. I'm trying to learn it. That's one remark. And well, yes, and maybe the last remark which I want to say, that well, this is a maybe just to finish. First of all, there is a well, something number 5. This is a number theory involved, and this number 6 is that one can try to figure out what is non-abelian generalization. And one expect from that what is called isomonodromic theta functions. Tau functions. And that, well, also I cannot say much about that, but well, it looks like that it should be the case. The only problem is non-abelian generalization, that for Heisenberg group, it's easy to write group extension. For loop groups for higher rank, there is no nice formula for central extension of the group. There are some formulas, but it's kind of very hard to work with them and to study them. But I hope that it's doable, and it's one of the subjects which I'm trying to figure out now. Thank you very much for your attention. I stop now.
Okay, thanks. Right, so any questions or comments? So I got one question. So you just mentioned those Hirota equations, right?
Right.
And Hirota equations, as far as I recall, these are some kind of quadratic equations.
Yes, it's just like, yeah, exactly. That's well, this is well, the Hirota equation follow from fermionic. Well, maybe I should also mention a very simple remark, that you can play the same game. Actually, there is another definition of tau function which is equivalent. Well, usual definition is of tau function is using fermions. Here is just the bosons, and you can play the same game with more or less. You consider, instead of Heisenberg group, you consider the group of well, you consider fermions, and also central extension. You have induced representation from holomorphic fermions. and you do all the same thing. And there, well, you have this invariance equation, this bosonic invariance equation star amounts to some bilinear, which is Hirota equation. And in this particular case, well, for this function, I can write down explicitly Hirota equation. They are differently bilinear, but this bilinear equation is comes from, well, it's fermionic analog of star. And of course, the main part of all this activity is just to prove that fermionic and bosonic formulas give the same function. So some functions like Hirota equation come naturally from fermionic, some like star comes from bosonic. But on the other hand, to compute the function, bosonic representation is usually much simpler. To write equation on tau function, it's easier to use fermionic case.
So are you saying it's not known how to derive bilinear relations from the bosonic perspective?
I don't know. I don't know, except that to prove that it's the same thing as fermionic.
Okay.
But on that hand, once again, it's just bosonic is just to compute the function, and the fermionic is just to derive equation of that. It's just kind of complementary approaches.
Okay. Any more questions or comments?
Sorry, I have a question about the relation with number theory. Because some notations reminds me, I don't know exactly, but for example, like the Adeli product or some, the Will reciprocity. I mean, what kind of relation with the number theory? Sorry, I didn't.
Well, I could say some stupid things because I'm not specialist, but roughly the relation is the following: that if you have one moment, I'm trying to you have one. I should have prepared this more for that because I didn't think about it for a while. But I could say stupid things. But the idea is that you have two elements. You have alpha and beta, which are some elements of p-adic fields in the p-adic field. And you have there is some symbol which is defined for alpha and beta. One little moment, I'll try to P, which is just some multiplicative symbol, and well, let me drop it. I'm sorry. I'm ready to explain it to you a little bit later, but I'm not.
Yeah,
I'll try to understand
let's postpone for a private discussion.
Yeah, it's for private discussion. Yeah. I cannot. I'm afraid that I'm.
Yeah, some easier questions.
Easy question, Volodya. Is it written somewhere?
It's written on a piece of paper, so I cannot send it to you. But.
Oh, okay. So it's a manuscript.
It's manuscript. Well, it's written in tech, but well, there are some coefficients which are wrong. Which are
modern manuscript.
Manuscript, yeah.
In the form of letter, it's very, very, I would say, high level attitude to exchange by letters.
Yeah, of course.
Well, very romantic.
Very romantic.
Maybe I should write also as well that it's supposed to be a thesis on my students, which is called for Riemann.
Hello. I don't hear you. You are writing. I see.
I'm writing. This is just there is a student with whom we work on that. So it's supposed to be a thesis. And for that reason, I'm not publishing it because, and I suppose that he's supposed to check the coefficients. So for that, I do not check it myself. So this is a reason why it's not published.
Good reason to wait.